So welcome everybody to the next International Prague seminar on function spaces. And our today's speaker is Angkana Rüland from Heidelberg University, and she will talk about rigidity, flexibility, and scaling laws. So Angkana, the floor is yours.
First of all, thank you very much, Lenka, for the kind invitation, and Lubos for the kind invitation to the seminar. It's really great to be able to speak here. So as Lenka said, I would like to speak about rigidity, flexibility, and some scaling laws motivated through some physical examples, through material science. But as the name suggests, function spaces will play an important role here too. Function spaces in particular will be able to distinguish between the rigid and the flexible regime, so they will indeed play a central role in distinguishing the situation. Okay, but before turning to function spaces and how they relate in this dichotomy between rigidity and flexibility, let me explain a little bit on the physical background that motivates the questions that I'm interested in, and where these type of questions come from. And please, at any point, if something is not clear, just ask and stop me. I'm more than happy to answer whatever question. Okay, so where do these questions come from? Well, these questions really come from applications, so from material science, where I'm particularly interested in certain materials which undergo certain very interesting thermodynamic behavior, and that they undergo a first order diffusion, the solid-solid phase transformation, in which symmetry is lost. And this loss of symmetry will play a major role in also the mathematical models. But let me first explain the physics behind it a little bit. So what happens is you have a material, a so-called shape memory alloy, which undergoes a phase transformation between a very highly symmetric high temperature phase. This is indicated here through this a square lattice. You should think of this is physically not entirely correct, but also not entirely wrong, as these points as the atoms of your physical microscopic lattice, and you should think of these unit cells as being periodically extended. And this is the phase the material is in the high temperature phase, the so-called austenite phase. Now, if you cool down the material, it transforms from this high symmetric phase into a less symmetric low temperature phase, the martensite phase. And it does so by reducing symmetry, for instance, changing from this very symmetric high temperature lattice to a less symmetric low temperature lattice, for instance, this rectangular lattice, which it could do by elongating the red, compressing the blue line. But there's no reason why it should compress the blue line, elongate the red line, because it loses symmetry. You immediately have different variants of the low temperature state. You could just as well compress the red line and elongate the blue line, yielding in this case two different variants of this low temperature phase. Okay, and so we will model this low temperature phase with respect to the high temperature phase. So these will just correspond to the deformation matrices, deforming the original lattice to this lattice. So in the first case, it would just be the matrix A0, 0B. But now, if you have such a material and you think of it in front of yourself, you rotate the material, or you keep the material and you rotate the chair, it should still be in whatever phase it was before, so there should not be a change in the material. So the model that we're interested in should be frame indifferent. So this means in particular that this variant of the low temperature phase is not only this one matrix, but the whole SO2 orbit of the matrix. Similarly for the second variant, and similarly for the austenite matrix, which would just be the SO2 orbit of the identity. Okay, and so in the setting you can easily imagine, just like with Lego bricks, that these low temperature lattices you can concatenate to more complex structures, and in fact these more complex structures that we are interested in, and where function spaces will enter in the description of these situations and these microstructures. So it's microstructures such as the one that you see here from experiments due to Tomonari in Namura, which are very, very complicated, that we're interested in. You see different colors correspond to different variants of martensite in this situation. You see multi-scale structures. So if you look at this carefully, you see structures nested within themselves, but you also see some kind of order in that these plates, the green ones are oriented in the same direction, the purple ones are oriented in the same direction. And understanding a little bit more on these structures is what, from an applied point of view, we are interested in maybe even predicting a bit more on these structures. Okay, so how should one model this mathematically more precisely, and how do function spaces enter? So mathematically, we're zooming out of the material, so we're no longer on atomistic scales. We zoom out and look at these materials from mesoscopic scales. Just in this picture here, you don't see the individual atoms anymore, but you have zoomed out already a little bit and only see the different variants in terms of some kind of average deformation. It's exactly this picture that we will adopt. So we will adopt a variational continuum mechanical perspective on mesoscopic scales, and assume that our material is originally in the high temperature phase given through some reference domain omega, and that its current state, its deformation, is described by a vector valued mapping U, mapping our domain R2 into R2, describing the current state. Then we will adopt a variational perspective following Ball and James, and presume that the material favors states of minimal energy, where energy in the simplest setting is just a function of the deformation gradient and temperature, the physics being captured in the stored energy density, which should reflect the atomistic picture we'd seen earlier. So it should be such that at temperatures above the transformation temperature, the austenite phase is favored, so the gradient wants to be in the SO2 orbit of the identity. At temperatures below the critical temperature, the two variants of martensite should be favored. The austenite is still a local minimum, but not a global minimum of this energy density. So you want to sit here or here. And at the critical temperature, austenite and martensite should be energetically equivalent. So you have three in this setting minimum or SO2 orbits of minima really that are present. Okay, and only by looking at these cartoon models, one also sees already quite some difficulties that are present in these models. So we see that all of these gauge groups are floating around. So there is certainly non-convexity coming from these SO2 and general SON orbits being present. So these variation problems will be highly non-convex due to that reason, but they will also, of course, be highly non-convex due to the reasons you see here and in the low temperature setting, that the material symmetries have to be respected, so that the two variants of martensite, for instance, are energetically absolute equivalent. There's no reason why one of them should be favored with respect to the other. So this variational picture that we have here from this Ball-James setting is a very, very non-convex, very, very non-quasi-convex even picture. Okay, and for that reason, it's a very difficult problem to deal with these energies directly. So for that reason, I want to simplify my life for the moment quite a bit. So I want to fix temperatures below the critical temperature or at the critical temperature, for the time being below the critical temperature. And secondly, I want to assume that we have very, very low energy in the sense that we have no elastic energy. So we're exactly stress-free, which means that the deformation gradient sits exactly in these two wells, so the SO2 orbits of U1 and U2. I want to understand what kind of structures, what kind of solutions arise in this situation, which is very much simplified, but I will try to drop these constraints during the talk. Okay, so the question then really boils down not anymore to a full variational problem, but to a problem of considering certain differential inclusions. So we want to understand what type of solutions arise for the deformation gradient. So U, a mapping, say, from R2 to R2, attaining values in these SO2 copies of U1 and U2. Okay, and obviously there are trivial solutions, so deformation gradient just being constant equal to one of these matrices. But obviously we would like to understand all solutions, the structure that can arise. And one particular class of interesting structures are solutions that you see here, in which the deformation gradient now is not a constant globally, but also it's not too complicated yet, in that it is a function of one variable only. So deformation gradient alternates between two values, let's say a matrix U1 and a rotated version Q U2 and so on, it being constant in this diagonal direction and depending only on the second diagonal variable. And so these one-dimensional constructions are not possible arbitrarily between arbitrary two matrices. Physically, you have to ensure that the material does not break at these interfaces. Mathematically, this just boils down to a tangential continuity of your deformation at these interfaces, which, if you rewrite this in terms of linear algebra, simply means that these two deformation matrices that are involved must be such that their difference is a rank 1 matrix, and you generically, for two wells, have that there are two possible rank 1 connections for one given matrix in the other well. So there are structures like these, but they are in a sense quite rigid, because the normals that can arise in these laminate constructions are rigid in the sense that it can only be the one diagonal or the other diagonal. So you have essentially two types of these laminates, but not more. Okay, so these are special solutions, but what about all solutions? We're interested in really understanding, classifying solutions of this differential inclusion. Now, of course, you could try to play a little bit. I mean, essentially, this was linear algebra, understanding the conditions at the interfaces. You could try to wonder whether you can come up with more complex structures from such linear algebra considerations. So you could look at corners at which 3 interfaces meet, or at checkerboards where there may be 4 different variants meeting, and so on. And for all of these, you could come up with linear algebra constraints, and you will see that none of these are satisfied. So corners of order 3, checkerboards, or more complicated corners will not be possible. Okay, so you could be led maybe to the conjecture that, okay, if you want to understand this differential inclusion, we actually understand it already. So apart from the trivial solutions, it's only simple laminates that satisfy this. And indeed, it turns out, and it is the first point where function spaces play a role, that this is correct if one makes a seemingly mild additional constraint, if the deformation gradient enjoys some higher regularity in the sense that it additionally has a BV control on the deformation gradient, which physically also makes sense. Physically, this would correspond to not having too many interfaces between the materials. If you assume this additional condition and assume that you have a solution to this differential inclusion, then indeed it's correct that up to boundary contributions, which are not so relevant, you are a simple laminate. So only structures of this type, and this indeed is an experimental picture from such materials from Bhattacharya's book, only these type of simple laminate structures arise. So only solutions which are constant in one direction depend on the corresponding orthogonal direction, and which are rather rigid in that only this direction or the orthogonal direction is present. Okay, but while this condition seems quite mild, physically reasonable, if you drop this condition, something very, very different happens. The situation changes quite dramatically. So if you drop this additional condition and still look at this differential inclusion and try to classify all possible solutions to this differential inclusion, it turns out, and this was found simultaneously by Dacoronia, Marcellini, and Müller-Schwerak with slightly different means, it was found that there are many, many solutions of this differential inclusion, far more than the simple laminate solutions. There's a plethora of very non-unique, very, very irregular, very wild solutions. So let me explain this more precisely. So whatever your domain, as long as it's reasonable, and you can find solutions to your differential inclusion with boundary data of your differential inclusion, which are in a quite large set in the interior of the lamination convex hull of these two wells. And don't worry about these lamination convex hulls. They are a kind of convexification of these two wells, convexification along rank 1 directions. But the important point is that this is a large set. So for a large set of boundary data, a codimension 1 set in matrix space, if these two wells have the same determinant, then for this large set of boundary data, you find many highly non-unique solutions of this differential inclusion attaining these boundary conditions. And in particular, because this set is so large, these solutions cannot all be simple laminate. So these boundary data in general are not compatible with the fact that for the simple laminate, the deformation gradient is constant in one direction. So these are many, many more, many quite different solutions from the ones we've seen before. Okay, so what are these solutions? So these solutions are obtained by these two groups with slightly different means of a convex integration scheme. So that's a scheme where you start with something which is not quite a solution. You modify this not quite being a solution by adding higher and higher oscillations, more and more fractal structures, if you like, and in the limit you obtain a solution if you can pass to this limit. An example of a numerical implementation in a slightly different setting is what you see here. Again, the color coding is such that constant color corresponds to constant deformation gradient. And you see already, you will see larger pictures of these and similar structures later, that the solutions after already 3 iterations are quite fractal, quite irregular. Okay, so these 2 results already show that there is a quite striking dichotomy appearing in this modeling of these material, quite striking dichotomy between extreme rigidity on the one hand, if you enjoy some regularity for your deformation, and very, very strongly flexible behavior if you do not have this regularity. Okay, so this dichotomy we see again here. So without any regularity constraint on your deformation gradient, apart from it satisfying the differential inclusion, which automatically, of course, means that it's L infinity, then you're very, very flexible, while at BV regularity, at physically reasonable surface energy constraints, you are very, very rigid in that only simple laminate can appear. Okay, but of course, this opens up a whole well, space of function spaces that one can consider this question in. The whole space or whole range of function spaces interpolating between the L infinity, the no constraint range, to the very rigid BV range. And you can wonder about a lot of questions. Of course, the physically maybe most important one to understand what this dichotomy that is present mathematically means in physical terms, whether it means anything in physical terms at all, or whether it's just an exciting but physically maybe not so relevant mathematical artifact. But of course, this is very hard to understand. Of course, one can wonder whether these type of structures that arise in the flexible regime appear also in experiments, and whether one can compare numerics with experiments, whether one can choose particular reasonable solutions among the highly non-unique wild solutions. But maybe mathematically most well-defined and fitting, hopefully, to the seminar best is the question whether you can have a kind of phase transformation between these 2 regimes. So the regime without regularity and the regime with regularity at some kind of critical function space, be it on a Sobolev or be it on a Bersov scale, where you transit from the flexible to the rigid regime. And a maybe more or less ambitious question is a question whether you can give some kind of bounds on what these critical spaces should be, in the sense that you can show that flexibility persists. So you can push from the flexible side, trying to prove that flexibility exists also at some kind of strictly positive Sobolev or Bersov irregularity. Or you could also just as well ask from the rigid side whether you can push from the rigid setting at lower regularities and still show that rigidity persists, thus, coming closer to these critical exponents. Okay, and from a more applications perspective, of course, this two-well problem, which I presented at the beginning, is in some sense a toy problem, but it's not unusual toy problem. So these type of dichotomies arise in quite a number of differential inclusions from, say, material science. Best understood is the situation in which you look at two wells with not equal determinants. So the O2 inclusion, where you have the identity and a reflected version of the identity, which physically corresponds to origami structures. Pardon? Where you have some physically origami type of structures where this dichotomy now really is understood, and where it's known that you can push up to BV and have the distinction at BV regularity scaling and rigidity at C1 regularity. So this is a quite well understood situation, but it arises also in many other phase transformations which are not two-dimensional but really three-dimensional, and arise in real experiments such as the cubic to tetragonal phase transformation or the cubic to orthorhombic, to name just a few. So it's really an interesting situation also from an experimental point of view. Okay, and so one can push, as I said, both from the flexible regime and from the rigid regime. In this talk, I would like to push mainly from the rigid regime, showing how function spaces relate to certain scaling laws and scaling law behavior, and discussing a particular example with the Tartar Square. But of course, one can also push from the flexible regime and try to see whether flexibility persists at positive Sobolev regularity. And so just to give a glimpse on that, I would like to start by explaining a little bit on the flexible side and then mainly turning to the rigid side. Okay, so what is known on the flexible side? On the flexible side, it is known as a first important step that flexibility persists indeed for interesting models at positive Sobolev regularity. So not only at this L-infinity threshold for the deformation gradient, but you can really show that there exists some positive S times P such that or some positive S such that at WSP you still are flexible. This was studied for particular model cases in two-dimensional and geometrically linearized elasticity first, but then together with Christian Zillinger and Barbara Zwicknagel, we have a quite now general framework that allows to apply this to both linearized elasticity, nonlinear elasticity, in particular including, for instance, this two-well problem, which was studied together with Francesco Della Porta. Okay, so we know that we can push from the flexible side. This flexibility persists for quite a number of interesting models. And in order to see how these solutions look like, we have also implemented them numerically. And here you see such an implementation similar to the one you've seen before. Again, color coding such that colors correspond to deformation gradients. So the gray thing is the boundary datum that we impose. And now this is a model with 3 wells. So the 3 wells are yellow, magenta, and cyan. And you see after 3 iterations, so this is not the full convex integration scheme, but really only 3 iterations of the scheme, you see that you're already quite good in the sense that you have large patches where you're yellow, where you're cyan, or where you're magenta, but you also see that the solutions are rather fractal, so that the solutions, at least that are constructed here, certainly don't have arbitrarily good Berzov or Sobolev regularity, but only some Sobolev regularity. And indeed, we have also estimated these numerical exponents that we get. Of course, we get analytic exponents within these frameworks, but there we are optimizing qualitative dependence, not so much quantitative dependence, because it's already hard to understand what kind of qualitative properties these should have. But I mean, for these numerical situations, we really have also quantitatively optimized the exponents. And for this particular construction, the exponent we get on H2 scale would be theta, I mean, the Sobolev exponent corresponding to 0.13, I mean, something which compared to our analytical results is actually not so bad. So it's a small exponent, but not so bad of an exponent. Okay, but of course, it's far from what one may hope to be critical or what one could guess maybe to be critical. So still, I mean, this picture where there's a lot of green maybe is the wrong picture to have in mind. So we can push a little bit from the left-hand side to see that we have some Sobolev regularity, but of course, it's an important first step to show that there is regularity. Okay, and of course, you can wonder about optimal structures as well. In general, bad news, we cannot make statements on optimal structures in general, but for very, very particular situations in which there is a very high degree of symmetry and where one considers very, very particular situations, we can indeed give some optimal constructions. And these optimal constructions rely on first work by Conti, Klar, and Zwicknagel, and then generalized by Pierluigi Cesana, Francesco, Barbara, Christian, and myself. These are situations in which one is two-dimensional, so physically maybe not the best situation, but also not irrelevant, as we will see in a moment. So where the deformation gradients are two-dimensional deformation gradients, and where they have a very, very particular structure in that you have a one-parameter family of deformation matrices, and then the other ones are obtained through conjugation, and where you have quite similar structures for very particular boundary data. So you always have identity or SON boundary data, but no other boundary data in that setting work, and where your solutions are some kind of self-similar nested structures, and which allow you really for these particular settings with particular boundary data, particular phase transformations, really to push to BV with these solutions. But again, very, very particular, highly symmetric structures. In general, we cannot make a statement on optimal structures and are very, very far indeed away from this. But in spite of this being two-dimensional, actually, it's physically also interesting. This is an experiment due to Manolikas and Amanix, where you really see these type of structures that here are also numerically implemented. And one sees that indeed, although our models are two-dimensional, they are not so bad also from a physical point of view, since there are really materials in which in the third direction nothing happens in quotation marks, and only the two-dimensional picture is the relevant one. Okay, so that much on the constructions, that much on the flexible side. So let me, for the rest of the talk, focus on the rigid side and how function spaces, critical exponents, and scaling may interact. Okay, and so the first question then is, can one guess scaling exponents? Can one guess critical exponents at which one may have a transition between rigidity and flexibility? And if one just looks at the differential inclusion, so the deformation gradient attaining values in these several SO2 or SON orbits of certain matrices, then one will see that there is no particular length scale present. I mean, if you think back of the simple laminates, it really didn't matter whether we have very coarse laminates or whether we have very fine laminates, both were perfect solutions. So there's no length scale present. And so there's nothing that allows to distinguish between these two structures. And in order to really now distinguish these structures and put regularity, put the function space scale into the game, what we're interested in are regularized versions of this, regularized in a similar spirit as one looks at, for instance, viscosity solutions in conservation laws or in fluid dynamics, but now on these elastic models. And one way that is very, very well known in the material science community, with many, many contributions, this being far from exhaustive, is a situation in which one looks at the elastic energies, which we had seen already in the Ball-James model, and adds some kind of higher order penalization. So this is a surface type penalization in which penalizes oscillations between the different wells in different forms, here in a diffuse interface form, but you could also think of sharp interfaces or some other mixed type of interfaces with a small parameter. And you're interested in the small parameter going to zero. But the combination of these energies indeed now gives you a length scale from the competition of the elastic and the surface regime. And there are chances that understanding that one can relate these type of energies to certain function spaces, to certain Bezos spaces at which something may happen. Okay, and this is indeed the case. So indeed, it is possible to prove that if you have lower scaling bounds for these energies in terms of the parameter epsilon, so if you can prove or could prove that these energies for a particular set K uniformly in epsilon for epsilon small have lower bounds in terms of epsilon to some power, let's say 2 mu, then what this would result in is upper bounds on the possible regularity of wild irregular solutions. So it would give an upper bound on the possible threshold between rigidity and flexibility. So more precisely, if you had a solution to this differential inclusion, and if you knew that the solution enjoyed some regularity, and here it's formulated on an L2 base scale, but if you change the energies to some BV or intermediate WSP scale, you would also be able to produce some WSP spaces here. But let's stick to the L2 scale. So if you knew that you had a solution to this differential inclusion with some type of regularity, then the best possible regularity would be strictly related to this lower scaling bound, in that it must be less or equal than this lower scaling bound. Okay, so where does this come from? Well, if you look at such a solution and think of the wild fractal solutions which we've seen earlier, then the solutions themselves, of course, will not be admissible competitors in these minimization problems, simply because these energies are too strong for this regularity in general. Okay, but while the solutions themselves are not admissible, you may just as well mollify or frequency truncate your solutions. So these modified or frequency truncated solutions then become, of course, admissible in your energies. You can plug them in, obtain them as competitors. And in this truncation in frequency or modification parameter, you can control both energy contributions. So the high surface energy term, the regularization term, of course, will become worse and worse as you let the modification parameter become smaller and smaller. So it will explode. while on the other hand, the modified solution will no longer be an exact solution of your differential inclusion, but will have some loss in elastic energy, but an energy that becomes smaller and smaller as this regularization parameter becomes smaller and smaller. So this term will improve, this term will deteriorate, and if you optimize this parameter delta in terms of epsilon, what you will end up with is an upper bound for this elastic energy in terms of epsilon to the 2s. And now you relate this to the lower bound. You obtain an upper bound to epsilon to the s. You have a lower bound epsilon to the 2 mu. This can only be true if s is less or equal than mu, giving this relation between this lower scaling law and the regularity of your possibly wild solution. So scalings indeed could possibly select some kind of, or at least give some kind of upper bound for the regularity of these wild solutions. Okay, and of course these energies are intensively and have intensively been studied in the materials science community. So there are many results on scaling properties for these type of energies. Typically they have algebraic behavior. One of the most famous results is the epsilon to the 2/3 scaling law due to Kohn and Müller first, but then many other results on scalings of this type. But also other type of algebraic behavior is known, epsilon to the 4/5, epsilon to the 1/2, which you can then always try to relate to some regularity of in function spaces. However, there's one caveat to that, in that for none of these situations where you know that you have scaling laws, lower bounds, upper bounds, is there really a dichotomy between rigidity and flexibility, as we've seen in the beginning. They are all too rigid to have this dichotomy between rigidity and flexibility. The closest that is known probably is a work by Alan Chan and Sergio Conti, who proved that if you look at the two-well problem, for which we know, we've seen that in the beginning, that we know that we have a dichotomy between rigidity, flexibility, then they prove a scaling law for a particular boundary datum, but this particular boundary datum, unfortunately, is on the boundary of the lamination convex hull, and for that, again, there's no dichotomy between rigidity and flexibility. You must really be in the interior. Okay, so the problem with applying this result to interesting phase transformation where you have a dichotomy between rigidity and flexibility is that if you have such a dichotomy, deducing scaling laws in general is very, very hard because the problem is so flexible. It's hard to deduce lower bounds on these types of elastic or elastic plus surface energies. Okay, so however, we want to apply this result to settings where one has a dichotomy between rigidity and flexibility. And so for that purpose, we simplify our model further. And the simplification that we look at is the model we see here, and which is something that goes back also to work of Ball and James, who proposed this also as models for these type of phase transformations, which are simpler because you don't have the SON gauge invariance present. So instead of looking at SON copies of certain matrices, we now look at a discrete set of possible matrices, so A1 to AN, and look at situations where the deformation gradient sits in place. Okay, and the question that we ask is whether we can characterize solutions to this differential inclusions, whether we can obtain scaling laws and thus conditions on critical function spaces, or at least upper bounds on critical function spaces that arise. And one can ask this question in two forms. One can ask it in the strong form, if you like, in the exact stress-free setting where your deformation gradient sits exactly in your wells, or in an approximate sense where you look at sequences that converge, say in measure, to your set of finitely many matrices, and you wonder whether the limiting structures, if you have limits, exist in the set to some extent. Okay, so if you like, this problem is really an inverse problem on the structure that gradients have. So it's a kind of question on the fundamental theorem in higher dimensions. How can you put together different gradients into an overall construction? And this, of course, is something that is has been studied extensively, starting with this work of Ball and James, who proved that if you look at two deformation matrices, and you presume that you exclude the, to a certain degree, uninteresting case that you have laminates, in that you ask this set of deformation matrices to be elliptic, in the sense that there are no rank 1 connections in these sets. Then the problem is rigid, in the sense that this deformation gradient must be either one of the matrix or the other, and these limits must be in the limit equal to one of the gradients or the other. A similar result for 3 matrices, always now for elliptic sets of gradients, so no rank 1 connections being present, was obtained by Schwerak and Zhang for 3 matrices, proving the same type of rigidity. But at n equals 4, something interesting happens, and something interesting that was studied and has been known for quite a while. Here there are some references. Maybe it's in PDE community, most known due to Tartar and his compensated compactness work. At n equals 4, there is a first type of dichotomy that arises in the following sense. So if you look at 4 matrices, then you find a particular set of 4 matrices, the so-called Tartar Square, which has the following property. If you look at the exact differential inclusion, then this is rigid. So all solutions must be constant equal to one of the 4 matrices. However, if you look at the approximate solutions, you will come up with a sequence of deformation gradients which converge in measure, but for which no subsequence in measure converges against one of these constant deformation gradients. So there is rigidity on the side of the exact solutions, but flexibility on the side of the approximate solutions. And even more rigidity is lost at n equals 5, which is work due to Kirchheim and Price, showing that indeed at n equals 5, even on the exact level, rigidity is lost. You have flexibility already here. Okay, and these settings where you have this loss of rigidity, flexibility, in particular, this Tartar Square is of interest not only for this inverse problems question, but of interest due to a number of other both pure and applied questions. For instance, these type of structures like the Tartar Square, related structures you can have in symmetrized symmetrized gradients, and for linearized elasticity already with 3 matrices as indicated here. These type of structures really arise also in physically relevant situations where you really have materials that have these kind of matrices as deformation gradients, as shown in the work by Chencha and Anja Schlömer-Kemper. Okay, and mathematically, of course, these Tartar squares have played a major role in all types of convex integration results, in particular, for instance, for elliptic systems. Okay, so for that reason, and because n equals 4 is the first situation in which you have a dichotomy between rigidity and flexibility, what we wanted to understand is whether the scaling result can be applied for the case n equals 4. So now exactly 4 matrices only, and we want to understand the scaling behavior of the energies which we've seen earlier. Okay, and indeed, this is possible. So if you look at elastic and surface energies of the type we've seen earlier, so the deformation gradient now attaining 4 possible values. The 4 possible values correspond to these diagonal matrices which you see here. So chi1 to chi4 are indicator functions which have mutually disjoint supports. And correspond exactly to the 4 matrices that form the Tartar Square. So it's the matrix -1, -3, and it's negative, and the matrix 1, 3, and it's negative. So these 4 matrices are preferred by the elastic energy, and we add a surface energy penalization, which now is a sharp interface model, but it really doesn't matter what type of interface model one puts for these type of scaling laws. Okay, and now in this setting, we can prove that indeed we have a scaling law for any boundary datum which lives in the interior of the rank 1 convex hull, which is a related convex hull, which is the interesting hull in the setting of the Tartar Square. We can prove that the energy of this type has a precise scaling law, in the sense that we have essentially matching upper and lower bounds with a somewhat unusual scaling behavior, which is no longer algebraic, but something between algebraic and logarithmic, essentially matching in that the powers of this log have a slight loss, which I will come back to later. Okay, so and the scaling is somewhat unusual in that it's not algebraic. This reflects the fact that in the Tartar Square one deals with infinite order laminates, so it's not only laminates as in these one-dimensional constructions, but you have laminates within laminates. So in the first laminate, you have more laminates and more laminates and more laminates, as indicated very roughly in this picture for 2 or 3 iterations, I guess. So the loss of algebraic behavior really is due to the fact that we're dealing with infinite order laminates. And secondly, in terms of function spaces, this is also interesting. This means this scaling law behavior is a scaling law behavior that is worse than any Sobolev space. So you could, on an L2 base scale, write down what type of growth you allow for your multiplier in the Sobolev space, and it is a multiplier between an algebraic and a logarithmic one coming from the scaling law. Okay, so this scaling law really now consists of upper and lower bound. Let me stress that the upper bound was something that was present in the literature earlier. So there had been work by Matthias Winter and Michel Chipot on these upper bound constructions for not exactly the same, but strongly related models in which they proved essentially this type of upper bound. So the real new bit of this result is the lower bound. And this lower bound is also in some sense a fun lower bound as it requires some kind of chain rule in a negative, in quotation marks, Sobolev space, which I would like to explain in a little bit more detail. Okay, so where does this lower bound come from? So we want to prove, I recall, that this energy has this lower bound. It's this lower bound that relates the function space, so these worse than Sobolev function spaces, to the scaling law. Okay, and in order to see where this should come from, let us have a look first at the exactly stress-free setting. So the stress-free setting was the setting where the deformation gradient attains values in these 4 matrices, so in the Tartar Square. And we know that's known due to Tartar and then generalized by Kirchheim and Schlebich, that you can indeed prove that there's rigidity for these type of inclusions. So why is that? Well, for the specific case of the Tartar Square, in fact, that's easy. So one first notices that these matrices are diagonal matrices. So in particular, this means that the del 2 u1 and the del 1 u2 derivative of your deformation vanish. This in particular means that u1 must be a function of the x1 variable only, the del 1 distributional derivative, hence also only a function of the x1 variable, and the 2 component a function of the 2 variable, only 2. Okay, so that is the easy bit. Then there's a slightly more subtle observation in this Tartar Square, which relates to the ellipticity of the differential inclusion, so of the set of wells. And it's the observation that the 2 component determines the 1 component and vice versa. So if you know that your deformation gradient has the value -3, you know its first component must be -1 and vice versa. So in other words, the u1, del 1 u1 component is a nonlinear function of the del 2 u2 component, of course, a non-unique nonlinear function. Okay, but this is enough and an invertible function, at least on these 4 matrices, we can revert this. Okay, but this is of course enough because we already know that the del 1 component is a function of x1 only, the del 2 component a function of x2 only, and this can only be the case if they're not a function of either x1 or x2, so they are constant, and thus rigidity is proved. And so it's this type of game that we would like to play also in the energetic and the quantitative setting. Okay, and so how does this game work on the quantitative setting? Well, on the quantitative setting, we have 2 contributions, the elastic one and the surface one. So the surface one is the one we've seen here again. Surface energy is always high frequency control. This means if you say that you control the surface energy, this means essentially there cannot be concentration of energy at high frequencies, only at low frequencies, of course, depending on epsilon. This means the only possible means of concentration of your characteristic functions is on a large ball, large depending of course on this parameter epsilon. So outside of this large ball, there's no energy concentration. Okay, that comes immediately from surface energy. The elastic energy is a little bit more complicated. So the elastic energy depended on the deformation and these characteristic functions, so the wells. One can minimize out the deformation and obtain an energy which only depends on the characteristic functions, and the chi1,1 component, chi2,2 component correspond to this one component and the second component. And write this down in a Fourier space in our L2 based setting, and obtain that this is determined by the Ries transforms in the one direction for the chi2,2 variable and the second Ries transform for the chi1,1 variable. But this means these two Ries transforms of course control the energy well if the multiplier is non-zero. So this means, in other words, this chi1,1 component can at most be localized in a cone along the k1 axis in Fourier space, and the chi2,2 component can at most be concentrated in this k2 axis and a cone around this k2 axis, to be precise, in Fourier space, and only at low frequencies because we have the combination with the surface energy. Okay, so we may have energy concentration in these two cones, and the game is to prove that there's no energy concentration in these cones, and to that end we want to use the second ingredient that we have. So in a sense, this first localization was a localization saying that the del1u1 component is a function of x1 only, that's this concentration, and the del2u2 component is a function of x2 only. Now we need to bring in this nonlinear relation into the game. And why can one hope that this is possible? The reason why one can hope that this is possible is well, I mean, if we had full control on, let's say, the function chi1,1 in terms of not only controlling the k2 Ries transform, but also the k1 Ries transform, of course, we control the full L2 energy, which means no concentration. So we want to control really not only the k2 Ries transform, but also the k1 Ries transform. And why is there a chance of this? Well, there is a chance of this because we know that chi1,1 is a nonlinear function of chi2,2. So if we want to understand the k1 Ries transform of it, we need to understand the k1 Ries transform of this nonlinear function of chi2,2. We understand the k1 Ries transform of chi2,2, well, not of the nonlinear function applied to chi2,2, but if you imagine that one could play a commutator game with this, then there's chances to also control this thing, and thus control the concentration of the full deformation. And indeed, this is what is possible, not maybe directly with a direct commutator argument, but we do this with an iterative bootstrap argument, showing that iteratively we can reduce the Fourier support of the two phases more and more through an iterated bootstrap commutator argument. Okay, but maybe let me not go more into the details, but let me emphasize that this type of bootstrap commutator argument can also be used in related settings, so not necessarily only the Tartar Square, but in settings in which you have different sets of matrices K in your differential inclusion, and you can interpolate, if you like, between these algebraic results of the very rigid setting and the less rigid setting of the Tartar Square by producing 4 different sets of matrices, different scalings, interpolating between algebraic and this not algebraic setting. And you can also look at this in more physical situations where you're really interested in nucleation results, for instance. But there are many, many more questions than answers, if you like, in this problem. So you can wonder about finer properties, you can wonder about selection mechanisms between these wild solutions. And of course, ultimately, it would be very interesting to understand also the relation with experiments, as the experiments I'd shown in the beginning. And okay, I think my time is up. So I thank you very much for your attention. And of course, I'm very happy about any question or comment.